Now, this is one of your new models.
This is it.
And you said off camera that we can apply the fluid to this one.
You're going to apply the fluid. You've got your fluid. This is water, so you have a conductive fluid, and we're going to apply it to the keyboard and system and see what happens.
This feels so wrong. I've had laptops since the early 90s, and this was a death knell for any of my first 10 years worth of laptops.
Let's give it a shot.
Achoo! How are gaming laptops tested to ensure that they can perform through all the wear and tear a user might bring on them? Alienware and Intel, the sponsors of today's video, invited us to Alienware's Extreme Testing Lab to see how robots, high-speed cameras, and even simulated cat hair are used to stress test their systems. Hey, Travis.
Hey, Adam, how are you doing?
Very good, sir. Okay, so this is the Extreme Computing Test Lab?
This is where bad laptops go to die, according to your words, right?
Well, so if laptops were sentient, they wouldn't want to come to this. This is where they get
You've got it. We are going to test them, abuse them, and ensure that those products meet what we expect our customers are going to receive.
So I'm sure you guys get a lot of damage to your equipment by users that is anecdotally reported to you, but this is where you structure that information.
Basically, we have built up a massive repository of data, and we use that data to build tests to basically simulate those harsh environments that our customers use our systems in, and then hopefully we build them strong and resilient so when they use it in the field, they have no issues over the life of the product.
Okay, the one I'm really curious about is there a test for testing about the laptop being yanked out of my hands when I'm walking out of the room and it's plugged into the wall?
Yes, we could talk about port yanking, we could also talk about dropping it, we can talk about, hey, your cat has decided to lay on the vents, and so we've got lots of options that we can show you today.
Let's get into it.
Let's do it.
This is so awesome. This is just opening and closing the laptop, what, hundreds of times?
20,000 times to be exact. So
20,000. That's how many you would run for a new model?
So every single system is actually tested to the same rigorous specs. And so we have a very broad-based spec based upon this hinge, because this hinge takes all of the loading. And basically, as you open and close it, it cycles that hinge. So we want to ensure over the life of that product, you don't have any issues opening or closing, putting it in your bag. If you put a pencil in it and close it, different type of features, we want to ensure that it's robust and rugged.
And you also, I'm assuming, want to see how it does over the course of those 20,000 iterations, those cycles, that it doesn't degrade, that its performance remains the same?
You've got it. So we are actually measuring torque of the hinge as this test goes on over time, and we can see degradation of that torque as it's loaded or unloaded to ensure that it's meeting our requirements and specifications. And this is different per panel size, right? So if you have a shorter panel, different weight, that changes the torque as you open and close. And so there's a ton of work that doesn't just go into the reliability of the hinge, but like one hand, two hand open, how you open the hinge.
And
so you have to do that. So
this is grabbing from the center, but you may also do this test from one side or the other side.
You can, and so we will show later tests where we actually grab it from a corner and we can test the strain and how it flexes over time to ensure you don't break panels, to ensure that the system is basically stable and robust.
I have to say, as an engineer who's built a lot of different things and a lot of different systems, a constant amount of torque on a moving hinge is maybe one of the most difficult problems I've ever had to solve. And you're having to do it on scales of millions, and you need that perfect operation.
That's right, and it basically it's a statistical distribution. So usually we have to collect a lot of data so we can ensure that, hey, this hinge, through the life cycle of a product, selling 1 million products, we're going to see this same type of profile.
All right, I want to move on over here to this one. Yeah. Oh my gosh, Travis, every one of these machines delights me. Is this really just experimenting with the torsional load of sticking your charger in?
It's charger, it's also USB keys, and so anything that you charge into the USB port, we have a very bad habit of taking a very thin USB key and putting it into a very heavy laptop, and everybody wants to grab the key and rip it out. And so in this particular case, if it's a charger, if it's your USB key, we are testing 8 different quadrants, 3,200 times, to look at the impact of that insertion and that torquing of that overall device. And so what this test does, it basically does a wrenching, so it pushes down at that different quadrant, and then it resets the overall test plate, and then it goes to a different state. And so we have had cases where people have pulled power cords, where you just pull on the cord, you don't pull on the laptop.
Well, I didn't mean to.
And so I can tell you, we would rather it be more robust instead of it break, because then it's actually, you know, a better value for Dell that we don't have to fix it after the fact. So we put all this effort up front and cost up front into building a robust port to ensure that you can go do that.
Oh my God, that's great. Okay, what's next?
Ready to go to the next one?
Yeah. All right, Travis, what are we witnessing here?
Well, like Tony Stark's robot, we got excited to use robots to try to simulate micro drop. So in this particular case, what we're looking for is the fact that, hey, when you take your laptop, how many times have you just thrown in a backpack?
All the time, every time.
And you throw your backpack on a table or a chair or a couch.
Yeah.
And so what we're doing is we're simulating different type of drop sequences. That was the first edge. Now we're doing a corner drop.
Amazing.
So every time you do this, these micro drops are focused on, hey, am I causing fatigue failure in the laptop itself?
Right.
And so we'll do every single side, front, back, edge, to give us that capability to see what it looks like and what it changes over time.
Travis, how many times will this robot drop the laptop?
So in this particular case, we're using the Aurora laptop from our gaming product, and it will drop it 1,200 times.
So you're doing this not with a stand-in laptop, you're doing it with a real laptop that you will forensically examine later.
Absolutely. Every single product is tested this way. Basically, we go through these micro drops, and later we'll talk about larger drops to go do this, but it really gives us that capability to simulate that harsh environment.
I love it. I love you keep saying harsh environment, and I'm like, this is just how I handle my laptop. I'm watching a robot be irresponsible with a laptop.
And every engineer cringes when we see that happening, right? That's the other piece of it.
But no, this is great.
Yep.
So you're building the cycles off of perhaps a reasonable assumption of the lifetime abuse of a machine.
That's right. So typically what happens is we have product everywhere in different regions, and we will capture that product to see how it's failed.
Right.
And then our reliability engineers will go in and characterize that data and build these tests. So this whole unit was built based upon what our customer feedback was based upon failures in the field.
So if a customer delivers to you a laptop that's a total loss and you replace it,
Yep.
the laptop that they destroyed is super useful for you guys in terms of damage.
Absolutely. So typically we do forensics. We capture those units, we take them apart, we look at how it failed and why it failed, and is there any key learnings? And honestly, we've been doing this for like 20 years, and so it's a wealth of data set that really gives us that capability to make a better product.
Amazing. I can't believe you haven't put googly eyes on it.
I may do that after this, actually.
All right, Travis, this is the yield test?
This is the yield test. So we call this our drop test. And this is basically to simulate when, hey, let's say you're sitting at a chair, typing on your laptop, and you stand up accidentally, or it slips off your knees and hits the ground. We want to simulate that type of environment to really try to stress it to yield, right?
Yeah.
These things are heavy, they're bigger. They have some mass to them, so we want to make sure that, hey, that robust chassis that we built around it is basically structurally strong and it doesn't really get a bunch of damage.
Now, you were saying with the mini drops that you were estimating the number of drops based on the sort of average life cycle of the abuse. I would assume that the iterations of this test are lower.
You're talking single digit tests. It's different per product line, but in particular, we have that tuned for like corners, edge, face. Every single one of these, we can change this machine where it's vertical, horizontal, on edge to look at those different conditions. But usually this is a lot of energy, rho GH, right? Potential energy. You're dropping that onto the surface. Additionally, we have correlated the base unit, like what it's hitting, rubber versus floor, to basic, where our customers using those products and what does that look like.
Now, off camera, you were saying that I could trigger this test.
You can. You've got the emergency button that you get to trigger and do the drop test yourself.
Super awesome. All right, 3, 2, 1. Ouch.
So we go in and we characterize that. We have high-speed cameras that you see where it's hard to see in this box.
Oh, amazing. Right.
So we can actually go through the frames and look at, hey, how much did it deflect? What did it do when it hit? And do we need to add structure anywhere in the chassis? And the other piece that's critical that really helps is we also check internally what happens over time, right? So in addition to drop, we do massive thermal tests where we're focused on the derating of the components and how they impact the product over time.
All the machines in this department sort of qualify, but I would imagine that this would be a laptop's version of hell.
It is a laptop's version of hell, and we really enjoy it because it's a conclusion of all the work that's been done. Did we meet our requirements? Did we meet the specs? And were we able to absorb that amount of energy on that product?
Now I'm looking at the surrounding space, and I see a lot of debris, and it brings up the question in my mind about dust and debris ingress in the machines. Do you have a test for that?
I want to show you that. I'm excited. It's going to be fun. We're going to use some cat hair and other media to basically damage the PC and see what happens.
Oh my God, let's go.
Let's go.
This is super cool. Travis, this is the dust chamber?
This is the dust chamber, the famous dust chamber. This is where we stress the system.
And I'm looking and I'm seeing fans, so I'm guessing when it turns on, it circulates, and this debris at the bottom is your dust?
Yep, that is our proprietary dust that we have developed for our particular products.
Okay, because this was my first question. I know that NIST, the National Institute of Science and Technology, will make like what they call like sample mayonnaise and other industrial liquids. So I was assuming that you got like NIST dust.
No, not in this particular case. So it is one of the actually harder challenges that we have. How do we ensure that the system is robust over time? And in this particular case, if you look at the dust particulates that we have, I'll give you a little bit.
All right.
It's a proprietary mixture that's supposed to simulate very common carpet fibers, pet hair and dander, what you see from basically a home environment or an office environment over time. Okay. So in the past, what we've done is we've gotten field captured, we pulled that dust out, we have characterized that dust, and then we've built our proprietary mix based upon those field captures from customers.
So somewhere at Dell is a bunch of little bottles of dust, and this one says, this one's from Denver of 2000.
Well, we used to. I don't know if we still have those, but we developed a dust spec in our particulate over time based upon that overall mixture itself.
Can we watch this go?
We can, and the thing to talk about a little bit in this particular case, these units are built with dust in mind. And so the foot height, the overall vent structure, if you look at the top vents on our Alienware products, that whole pattern is basically designed to ensure that those particular dust particles have a very difficult time going through it.
Making a right hand turn.
So if you looked at like a 1 millimeter diameter hole versus the dust average fiber length, it's very hard for it to go through the particular hole. Okay. So if the hole was bigger, you're going to have more dust ingress. And so from that, that's what we've developed over time in the structure of the system itself. And so let's turn this guy on. And it's going to suck this up over time. It's going to increase temperature. And you can see the particles basically blowing through the unit.
Oh, this is awesome.
Yep. And it's going to accumulate a lot of dust. This is an accelerated life test. So what we're trying to do is basically illustrate this dust collection over time. Now what you're seeing, look where it's actually being captured.
Right, on
it's
either side
of the dust.
Yes.
It's on top of the perforation. That's exactly what you want to see. We don't want to see it in it, but what you want to see it is on it, because it's almost like a filtration mechanism to keep that dust out of the system.
Are you also, is the laptop itself running self-diagnostics on components that may get overly hot because of dust?
So we do have the capabilities, and this is honestly a little newer for us. Within Support Assist and some of these other features we have in our programs across our product line, we can look at the thermal telemetry across the stack. So it goes from OS to CPU such as Intel. Intel has a great driver stack that shows us exactly what's going on in the silicon over time. And they've got something called DTT, which is their dynamic tuning technology driver that we can tune to. We pull that information in. Then we have the base system information. So we're getting OS component system data at runtime that we can diagnostically look at this system over time.
Oh my goodness. Are you ever running this test and the laptop just shuts down? Because it's...
Not anymore. Okay. Like a long time ago, when we first started this, we had to do those collections because that's exactly what happened. We pulled the back of the system off and looked at the heat sinks, and it would just be completely caked, 80% coverage. That whole pattern, if you look at when it was optimized, we were actually able to cut that dust egress over that same amount of time by 60%. Just by changing the hole size.
Amazing.
And that will be a continuous area of focus for us. So you're going to see more innovation in the future in that. And it's all about, hey, I want to get air in the system to take the energy out of the components while keeping all the bad stuff out.
And so I'm sure like some people would say, why not just put a HEPA filter behind that? But you're working in exceedingly tiny spaces.
You are. And so there's a counter to this. It's thermal. So the fan performance is also a function of that hole size. And so what we want to do is have as many holes as I can, as small as I can within that area. That gives us maximized flow while maximizing the filtration at the same time.
So then I would imagine that advances over the past few years in micro machining are also to your benefit in terms of the geometry of those holes in the future.
Yeah, micro drilling is a big one, right? Lasers potentially. It gives you the capability to really look at the physics of the hole.
At this very tiny...
Now there is a limit as you get closer, right? There's basically a region of the wall. It's a boundary layer where air isn't moving. If you keep going that hole so close, it jacks up the pressure drop. drop, and so it takes a lot of force to push it through it. But this system, from the vent on the top, the vent on the bottom, the foot height, in this particular case, this is actually worse because it's so far off the system, dust can go on each side. In a real system, you're only going to have like say a 5 to 7 millimeter gap to the base of the system. You're not going to have as much ingress of that dust in that particular case because of a solid table.
So it's the worst case scenario.
This is the worst case scenario. We're running a centimeter stress, maximizing dust, blowing it in a chamber positive, in a 28C ambient right now within the system.
I love that it's clear plex. Those were always my favorite.
Yeah, you can actually see it, right?
Yeah. Okay, so this is the dry. You know, I have spilled a lot of liquids on my laptop over the years. Do you have some spill tests?
We do. Let's go check out our spill test, and we'll let you probably dump some water on something.
That sounds
good?
awesome and horrifying. From dry to wet, this is your spill test. This is, I don't know what I expected, but after all of these robots manipulating computers, I thought this would be a little more something.
Something automated? No.
Yes.
In most cases, what we see with like customers, you have a can of Coke, you've got your tea, wine in particular, and when I'm gaming, I'm usually slamming a mouse and keycaps, and I hit something, and guess what? It knocks over onto the keyboard itself. So this setup, because it's a little dirty and we use different fluids, we typically do this old school where you can set it up and run the test. The interesting thing is most of our products, when we engineer them, we're looking for how the fluid basically exits the system. So when you apply it, we've got a die that actually lets us trace the fluid as it's going along the fluid flow path. So this is how we learn. So in particular, what you're looking for as fluid goes onto the keyboard or the system itself, does it have a natural path out? And the way we manage that is we apply the fluid, let it dry, and then we can trace that pathway to see, do we need to make something more robust? Do we need to change the fluid pathway out of the unit, off the keyboard, etc.?
So you will investigate where that die has gone in order to learn where you need to protect the innards from the liquids.
You've got it. So we could use like Mylar shielding, or do we change the chassis, or do we change like the whole pattern to allow that fluid out in a certain location when it's flowing within the unit itself?
And I'm also guessing from a cost-benefit analysis, you're not trying to armor the entire thing against every possible liquid. You're trying to do it where it's strategic so you're not overdoing it.
Like, I mean, if you take extreme products where you encapsulate the whole motherboard, that gets extremely expensive. You can do those type of things, but it's more of like a very niche product. But in this particular case, we are ensuring that, hey, when you apply a fluid, it's going to basically dry out and the system will reboot if it does, and then it gives you that capability to use it again and again.
Now, this is one of your new models.
This is it.
And you said off camera that we can apply the fluid to this one.
You're going to apply the fluid. You've got your fluid. This is water, so you have a conductive fluid, and we're going to apply it to the keyboard and system and see what happens.
This feels so wrong. I've had laptops since the early 90s, and this was a death knell for any of my first 10 years worth of laptops.
Let's give it a shot.
Achoo!
And so in this particular case, you see how the fluid's rolling off, right? So what we look for is how does it exit the keyboard? How does it exit the system? So what you're seeing is the membrane of the keyboard and the keycaps, those have cracks in it that the fluid goes in. It comes out that base and it's basically draining out the system.
So the back of the keyboard is a membrane that's scooping that water and allowing it to
usually,
flow.
So all of these have there's a stainless steel plate, there's a membrane, usually it's rubber dome or there's clicks underneath this that gives you the capability to route the fluid out. So in this particular case, you're drying out the system, and then we'll basically let it dry and you can shake it out to get the rest of the fluid out and off you go.
I cannot believe it's still running. That felt so awful.
We don't want you to do that. That is not a common use case. You don't want to be in the bathtub playing with your laptop, right, and splashing it. But we do harden these things to ensure that you get this type of ruggedness and capability.
Travis, this has been the most fun torture chamber tour I have ever been on. Thanks for letting me abuse your laptops.
Anytime. Thank you.
Amazing. All right, Travis, tell me about the department we're in right now.
Great. This is our acoustic lab. So this is where we test all of our systems to make sure from a noise spectrum perspective, it's a pleasant sound and it's meeting all of our specs.
So you're testing the laptop for, I'm sure, would be fan sounds, but also the quality and fidelity of the audio it's putting out on purpose.
That is perfect, exactly. So we're going to be studying sound loudness and particularly sound pressure. And then we're going to actually look at some tones with a low noise mic on the system itself.
Now, that's looking through this door and I see what looks like an anechoic chamber, which I love these kind of rooms.
It's very close. It's a semi-anechoic chamber. So basically there is not a floating floor, but basically every other surface has the capabilities to absorb the sound. And so really what we want to do is make sure the sound coming out of the system is going to go to the sensors in it.
Okay.
And so we capture that at a specific location where the user is going to be typically at using the laptop.
Can we go in?
Let's go.
Okay. I love these kind of chambers.
Yeah, we call it the spooky chamber.
Dude, it's so immediate how quickly things get weird.
Yeah, it's super quiet. I mean, all that noise that we're talking is going into those overall structures on the walls.
Yeah.
And then there's foam that absorbs the sound waves, right? So it's frictionally absorbing it and creating heat. And so that way the noise doesn't reverberate back to you.
Can we close the door?
Yeah, let's close the door.
Oh,
Yep.
look at this door. Absolute unit.
So now you are stuck in the room where we do our testing.
Okay, so I'm seeing a head, which I'm assuming has probably some microphone elements in it.
That is a good guess, very good guess. In this particular case, we use head acoustics, and it has 2 mics, and so basically pressure mics in the ears to simulate the user at the location. There's an ECMA standard that most PCs use that is 0.5 meter distance from the basically front face of the head to the front edge of the system itself on center, and that gives us the capability for a typical user space of the distance from the system to the microphones themselves.
Now, this is matching the topography and spacing of the way our ears work. Is it also matching the density of a human head?
It does. And so the density, the structure, this is typical average person as far as the overall size and the spacing between the ears, because that is important. As that wave comes out, it's almost like if you think about if you're on the water, that wave, if you threw a rock in the water, how it propagates, it does the same thing. So as the noise hits each ear, how is each ear hearing that? And it gives you the capability to measure it in sound pressure, which we convert to sound loudness. That's a psychoacoustic term to determine how you think you hear it with our software on the back end.
Now, given that you make all sorts of different machines that produce intentional and unintentional noises, is there an idealized sort of uber sound profile you are hoping to hit?
There is. And so typically from a noise value perspective, there's an absolute pressure at the user's ears that we want to target. And it is different per line of business.
Okay.
Gaming,
I was wondering about that.
Yeah. So gaming, typically gamers want to be more aggressive on performance. And so typically they're more accepting for a little higher noise. It's not a lot, but you're going to see from a product category.
Oh, they'll take the trade-off.
They'll take the trade-off, typically saying, hey, I would rather have my system cooler for, say, loudness that's slightly louder. And so in this particular case on our systems, we give a lot of tunability to the customers. You can put it in what we call performance mode or the high-end ultra performance mode. It's full fan speed. So this system can go up to 8 zones.
Okay.
Typical operations 4 zones. And basically you're going to have that difference per line of product. So a Dell, right? Or a Dell Pro or a Dell Pro Max would have a different spec depending on that product.
Right, so their different customer bases may prize sound fidelity over performance or vice versa, and this is the test that helps chase that down and figure out. So I guess if they're willing to accept more noise for performance, that gives you guys a lot more flexibility in terms of how hard you can drive that machine.
We can, and also we give the customer choice. So if the particular customer doesn't like that, we have a cool and quiet mode that they can enter into, which actually drops it down to about 30% less than that. And so you can really have this infinite tunability, and this is true across all of our products, from Dell Pro up to Alienware, that you give that customer the choice to pick, because the reality, this is hard, because they call it psychoacoustics for a reason, because
it's very subjective.
It's subjective, right? What may be loud to you may be quiet to me, right? And so we want to give them the choice that they can pick those trade-offs, and it does impact other attributes like performance of the system on frequency and duration of frequency.
Just enjoying how dead this room is. I would nap in here.
You pull up a hammock?
Do you know, does anyone in the company come in here and nap at lunchtime?
You know, this isn't the dungeon of the lab, so particular, I hope they don't, but I wouldn't blame them for it, right?
Neither would I.
And I can tell you at night, it is kind of spooky. If you're here by yourself with this noise, that gets to be an interesting scenario.
Oh, the ears are actually flexible rubber.
Yeah.
Okay,
it's
so they're matching.
It's similar to the structure of your ear.
So the density of the cartilage in my ear. Amazing.
And so all of this is really, as that wave propagates out, right? It's going to propagate out, hit the ear, then it's going to come down the channel into the
like it does
into the diaphragm,
ears.
into the pressure transducers, and those pressure transducers is what picks up that overall signal that we run back to the data acquisition system to do the calculations. So all these wires are all about taking these signals back to the computer to do the calculation.
There's microphones in the head. What is this extra microphone
So this is a low noise mic. If we're trying to pick up like really like a squeaky noise, like a high frequency, low power noise, you have to use a different mic. So this is a much bigger diaphragm of a pressure transducer. And we typically can do it 15 centimeters off the surface to identify, is there any weird noises coming off of like a capacitor, stores energy.
Yeah.
And there's two plates, right? Those plates can vibrate.
Okay.
If they vibrate, they can actually create a noise off of it that's really high frequency and pitchy. And so we're looking for those type of attributes.
I would imagine too that this could give you places to look for improving the actually exterior structure, the way it encompasses the components and the sound.
You are spot on. So in this particular unit, a big one is the intake vents, the exhaust vents, and the foot height. So in this particular case, we talked about this a little bit with dust, but it's also for acoustics. And so how you structure the vent pattern allows that noise wave to propagate out into the mic, right? Similarly, the foot height can dictate how much air is coming in and the pressure drop along that, also the velocity. So all of these different attributes come into play.
And they will change the sound profile.
They can.
That comes out amazing. Dude, this is so awesome. Can we run a test?
Absolutely, absolutely. Let's do it. We're gonna start Cinebench R23, and then we're gonna go measure the acoustics.
Okay.
So let's go do it.
Okay. Amazing. These are the results of our test?
These are the results.
Okay.
And so if you look here, we've got our sound power spectrum and sound loudness, specific loudness. This is the one that's the most important.
Yeah. And
typically what we see for a product under stress is about 3 to 4 zones, and the left ear was 1.6, the right was 1.43, and we always use the highest of.
Okay.
So this measurement from that particular system was 1.6 zones.
And you'd be looking for something a little more under ideal circumstances.
That's right.
Okay.
So in particular, this tells us that we have a headroom, we have margin on this particular chassis, and that was running Cinebench R23 100%.
How many times will you run this test?
So we'll run this through a range of applications. We'll do idle, typically a productivity applications. We'll do like what we call a thermal stress plus firm arc, so CPU plus GPU 100%. But it's usually a range of 3 to 5 test conditions, and we'll run it at different ambience. So 23 setup and a 35 could have different RPMs that we run at that condition.
And you also might test it in other rooms for other sonic properties.
We do. So we also do sound power, which is in a separate room, which has an array of mics.
Amazing.
And typically, this is how we do the calculations, and it gives us, are we meeting our specifications? And when we do reporting to government agencies, we use these same type of tools to report the sound loudness level.
Amazing. Can we go back in one more time?
Yeah, let's go.
Okay. I didn't have anything else to do. I just want to experience the room one more time.
It is cool. It is cool.
And just the next time I come, can I take a nap in here?
Yes, you can. We'll let you take a nap. I'll set up a hammock.
Oh man, Travis, thank you so much.
Thank you. Appreciate it, guys.
So illuminating. Thanks so much to Alienware for having us in their labs to learn about how they test and iterate the designs of their systems. You can find out more details about Alienware's gaming laptops in the links below.